Let's talk about saddle node bifurcations. These are really common and they're a really interesting type of bifurcation in which a pair of equilibrium points suddenly appear. Some people have described these as blue sky bifurcations because it's like all of a sudden a pair of equilibrium points just shows up out of the blue and then it's in your system and it might kind of mess things up. In fact, it has been a good way to explain a crazy situation in which these insects called spruce budworms overtake a forest and they show a sudden outbreak in their population with an extremely high population, and people are like, hey, where did all these spruce budworms come from? Well, they appeared out of the blue through a blue sky bifurcation or saddle node bifurcation. Okay, so we're going to use the example of the spruce budworm outbreak to illustrate what we mean about this bifurcation. And bonus, you're also going to get introduced to a new type of analysis, which is called the over-under method. And this method allows us to analyze one-dimensional systems whose function f of x are a little bit too complicated to really want to take on with the entire thing. So we're going to learn a new type of bifurcation and a new method to analyze one-dimensional systems in general. All right, so let's start with an introduction to the model. Luckily, it starts somewhere familiar because the rate equation for the one-dimensional population starts with just our classic logistic growth term in which we have the continuous growth rate and the carrying capacity in the usual places. But then we have this term where we're minusing away. We're taking stuff out of the population. And it's supposed to represent predation, I think particularly predation by birds. And what it is a density-dependent predation term. So instead of just being like a constant term where we're saying some constant amount of the population is being preyed upon per time unit, instead we're kind of in a situation where maybe I could just read it out of the book. It's kind of fun. It says, they're preyed upon by birds. When there are very few budworms around, the birds don't hunt them much because they're focusing on other prey. But as the budworm abundance rises, so does predation. Unless there are so many budworms that all the birds have eaten their fill, and an increase in budworm abundance does not bring an increase in predation. Okay, so that whole story is being told by this term right here, this density-dependent predation term. Just for a minute, I want to give you a snapshot of just what this term looks like in a graph so you can understand that little story that I read. Okay, so I'm just going to take a snapshot of x versus, I'm just graphing this one function on the y-axis. And if you remember pre-calculus fondly, you might describe this as a rational function where we have the ratio of two polynomial terms, and this happens to be one of those rational functions where the order of the poly on the top term is the same as the order of the polynomial on the bottom term, which is going to result in a finite horizontal asymptote. So as x gets larger and larger, where does this function tend toward? See if you remember from pre-calculus. Yeah, the horizontal asymptote is located at the ratio of the leading order coefficients. In this case, it's 1 over 1, okay? And when x is equal to 0, you can see that we have 0 on the top and 1 on the bottom. So this right here is a function that varies smoothly from being 0 when x equals 0 to eventually topping off at some horizontal asymptote at 1. Okay? That's just a snapshot of this function, and so I want to match that with the description that I just read. It said that when the density of spruce budworms is low, the birds don't bother to go pick around and try to find them. They're focused on other prey. So when the species is low, the predation term is low because they're hard to find. Then, as the species gets larger, the predation goes up as well because they become easy to find. But at some point, when there's so many of them around, the birds are like, what do you want to eat today? More budworms? Nah, I'm good. I have enough budworms. And so the predation term kind of tops up at 1. Like this is the most budworms that the birds are willing to eat. Even if there's more of them, they're not going to prey on them additionally. So that's the whole idea behind the density-dependent predation term, and that's what's really going to make this really interesting dynamically. is having this complicated term. I mean, it's super fun that we have this, but I'll be told, if I was going to make a graph of x versus x prime here, having this and that combined is just a little too much for me to kind of graph easily. And so I'm not going to do my usual thing where I make a graph of x versus x prime. Instead, we're going to do a little trick, which is called the over-under method. Okay? Now, the first part of this trick for this particular model is that we notice that both of these terms have a common factor of x. And so here you see I've taken the same rate equation, but I factored out the x term. Remember that we've done that before, particularly for two-dimensional systems, because then when we set this whole thing equal to 0, remember we want to set this whole thing equal to 0 to analyze the equilibrium points, we can just do it one factor at a time. Okay, now the easy factor I kind of did for you, and I'm not going to do that one in the video, but the easy factor obviously is this one right here, x equals 0. So that means x equals 0 is always a fixed point. It's always an equilibrium point. If you did go through the linear stability analysis, you would conclude that 0 is always an unstable point. And so anytime I draw a phase line of this one-dimensional system, I'm going to see an equilibrium point at 0, but through further analysis, I will know that fixed initial conditions that start above 0 are going to tend away from 0. So 0 is always an unstable fixed point, equilibrium point, and the work for that is not on the board, because what I want to do on the board here is focus on what's left, the not easy stuff in this big, long other factor right here. Okay, I'm pretty good at graphing lines and simple stuff, and so what I'm going to do is I'm going to recognize the fact that this first term, which is what's left of the logistic term after you get rid of the x there, is a line. This is a line with a negative slope here, and it has a y-intercept of r, and it has an x-intercept at k. Okay, so I'm just graphing the blue part, just the top part that represents the logistic growth term without the factor of x in blue. All right? And then the other term that's getting subtracted from that, the density-dependent predation term, I'm going to graph what's left of that after I pull out the x in red. And so what you see here is this hump. It's not the same thing I graphed before. Remember when I made a little graph over here of this term? Well, that was when I had x squared over 1 plus x squared. But after I factored out the x, and I'm only left with x over 1 plus x squared, I still have a rational function, but remember that when the leading order on top is less than that of the one on bottom, that rational function is going to have a horizontal asymptote at 0. Okay, so the red term is this term right here after you pulled out an x, and so it looks like this little hump instead of that sigmoid that I had drawn before. Why did I bother splitting it up into a blue term and a red term? Trust me, it's going to be easier for me to analyze if I do it this way. And if you don't believe me, you can pop open Desmos and you can graph this whole thing in Desmos, and then you see if you can determine where the number of roots is going to change. I did it myself, and it wasn't that easy. But an easier thing to do is going to be to open up Desmos, or just look here, and graph the blue term and the red term separately. And because I want this factor to equal 0 in order to reach equilibria, now that I have the blue and the red separated out, the places where this factor in its entirety will equal 0 are the places where the blue line and the red line intersect. Okay, so you'll notice that on this graph, I'm labeling the x-axis with x, the state. Usually on a graph like this, the y-axis would be labeled as x prime. But this is not a graph of x prime. This happens to be a graph of just two components of one factor of x prime. And that's so that I can focus on how the interaction between these two factors changes as I manipulate the parameters involved. I know it's a little complicated, but it's going to be worth it because it's going to help us visualize the saddle node bifurcation. Okay? So I've drawn one instance of a situation, but there's actually going to be 3 qualitatively different situations, and that's why I have 1, 2, 3 phase lines all ready to go here as I start to describe the different situations. remember that I said that 0 is an equilibrium point, that it comes from this factor over here, and it's always unstable, although you're not seeing the work for that on the board. Instead, what we're going to do is analyze what this graph tells us about the location of the other fixed points, of the other equilibrium points, and it's actually going to allow us to analyze the stability of the equilibria that we locate using this new logical method that's called the over-under method. Okay, keep in mind that x prime, the factor of x prime here, is blue minus red, and the equilibrium point where this factor, this whole entire factor is 0, is located where the blue is equal to the red. Because if the blue is equal to the red, that means that this difference is 0, and that means this whole thing is 0, and that's what leads us to equilibrium points. Having said all that, can you see the equilibrium point, the other equilibrium point besides x equals 0 appearing on this graph? Yeah, it's right there. It's the intersection between the first part of this factor and the second part, right? So that's the equilibrium point, right? Right there. It's going to be an equilibrium point, and that's going to be some value of x which is greater than 0. And so this is my case. This is what I'm going to call case number 1. And I'm going to eventually end up with 3 different cases, and so I'm going to label the different cases down here. This will be the phase line for my case number 1. All these cases have 0 as an equilibrium, but case number 1 here also has this other equilibrium point. And remember, this horizontal axis represents the state. So the other equilibrium point is close to but greater than 0. And so here's the other equilibrium point right here that I found right here. Okay, now is this going to be a stable or an unstable equilibrium point? There's different ways to reason that out. One way would be the quick way of saying, well, you told me 0 was unstable. So, of course, lined up on a line, the next thing that is an equilibrium point must be of the opposite stability. So because 0 is unstable, I conclude that this one is stable. Sure, that's one way to do it, but pretend we don't know that so that we can use the over-under method. Okay, so in the over-under method, we're going to try to reason how the sign of the rate equation x prime changes as we travel less than, equal to, and greater than the location of the equilibrium point. Okay, so here I'm just going to mark off the x star. This is the equilibrium point that we're talking about right here, marked as x star. Okay, and remember how I had this little arrow? Let's pretend I didn't know this. I don't know what the stability is, and I'm going to try to reason that between 0 and x star, is my rate equation a positive number or is it a negative number? That's what the over-under method is going to tell us. Okay, well, the whole rate equation is x prime, right? And x itself is positively valued because x represents some kind of population. So I know that this term is going to be positive. So what I need to do is use this graph to try to figure out if values of x in this area right here result in a positive or a negative value for x prime. Well, that basically has to do with which term is bigger. Is the blue term bigger or is the red term bigger? Because if the blue term is bigger than red, then big minus little is a positive number. But if the blue term is less than the red, then little minus big is going to be a negative number. Does that make sense? So I'm actually going to determine the sign of this entire factor just by looking at who's on top on this graph. Is blue bigger than red or is red bigger than blue? That's what's called the over-under method. So who's over and who's under. Okay, so in this region right here, where x is between 0 and the equilibrium point that we recognized, what do you think? Is x prime positive or is x prime a negative number? You see, the blue is over and the red is under, and so blue is bigger than red. So this difference, blue minus red, is going to be a positive number. And so in this region right here, I'm just recognizing the fact that blue minus red is a positive number. So x prime is positive times positive, and so it's positive dynamics. X is moving to the right in this region, And so I can draw that on the phase line horizontally here, or I can mark that on the phase line in the vertical description right there. That's what I already knew because I told you 0 was unstable before, but you see, this is us using the over-under method, which is going to come in very handy. It's better than taking the derivative of all this junk and then trying to find an algebraic form of the fixed points and throw it in there. You don't want to go there, trust me. Okay, so now what we have to do is just determine what the sign for case 1 of the x prime equation is going to be when x is greater than the fixed point. Okay, once again, using the over-under method of our logic, we're just going to say who's bigger, who's smaller, and is this factor positive or negative because of that. Okay, now the red term on this side of the line, the red term is above the blue term, so that means this one is bigger than this one, and so it's little minus big, which is a negative number. So we have a negative factor here. We still have a positive factor here because the state x is representing positive values, and so we have positive times negative, which is negative. So it's pointing down from above. I could label that there, or I could label that right there. Great, so what we determined here for case 1 is that this x star right here is a stable equilibrium point. Like I said before, 0 is unstable, and 0 is going to remain unstable for all the different cases. Okay, but, I mean, all of this hasn't bifurcated at all yet, and the topic today is saddle node bifurcations, in which a pair of equilibrium points suddenly appears out of the blue. And really, I told you I was going to tell you a story about Outbreak, but when you kind of look at this graph, you notice that the only equilibrium point here is one such that x star is not that much bigger than 0, and so with a population level up here, I wouldn't really call that an outbreak. Keep in mind the carrying capacity for the population is all the way over here, right? So the carrying capacity is up here, and yet the population's all the way down there. That's not an outbreak. So where's our bifurcation? Bifurcation is going to show up as we manipulate the parameters r and k. So we take this blue line and we move it in such a manner that it starts to intersect this part of the red line. Remember, intersections of the blue and red line locate equilibrium points for our system. Okay, so that was case 1. I'm going to erase case 1, and I'm going to give you a new case to consider now here. As I change the case, I will have inevitably changed the parameters a little bit, and so that's why I erased the label of where k was, because I'm now going to be changing the whole situation. Okay, so I'm kind of erasing what I did before. And now I'm going to say, maybe I should use an eraser. Now I'm going to try to draw a blue line that intersects the red line in a different way. Not just once, but twice, or dare I say it, even 3 times, because a pair of equilibrium points is what's supposed to appear out of the blue. Okay? Actually, the case where there's 3 points is easier to draw than the case where there's 2 points because there's more ways to draw it. Can you think of a way that I could draw a blue line here that's going to intersect this red line 3 times instead of 1 time? Maybe if I drew it like that, and I kind of made it like that, now you see that I have 3 places where the blue and the red lines intersect. They intersect here, and over here. So now, this is case number 2 now. Case number 2 has 3 equilibrium points. Really, there's 4 equilibrium points technically because 0 is always an equilibrium point that we kind of started it out with. But 3 equilibrium points come out of the analysis of having this factor set equal to 0. Wow, that's a lot of equilibrium points. How are we going to analyze the stability for all of those? Well, first, let's just label them on the phase line, and then we'll go one by one, and we'll use the over-under method to determine their stability. Okay, this is going to be case number 3 over here. And this is going to be the case that's past the bifurcation value, and then we'll talk about case number 2, where it's right at the bifurcation value as the last case. Okay, did you see? a pair of equilibrium points suddenly appear out of the blue. That's the blue sky bifurcation. First we had a line that was going like this, and then we tilted it in such a manner that these two equilibrium points just showed up out of nowhere. And compared to the value of x here, here's the first equilibrium point, x star. Here's another one, another x star, and then here's a very third one all the way over here. These two equilibrium points that appeared are at quite larger values of x than case 1, where I just had the little value of x that was a little bit bigger than 0, right? So on my phase line over here, I'm going to mark the first equilibrium point. So what I'm marking right here is equivalent to this one here. Let me label them for you, actually. So this is going to be equilibrium point number 1, number 2, and number 3. Okay? So equilibrium point number 1 is there, equilibrium point number 2 is there, and equilibrium point number 3 is there. And you can see that I've gone through some kind of qualitative change in the system. I used to just have these two equilibria, and now I actually have 4, counting 0, and I have 3 that are coming off of this term up here. Let's use the over-under method to practice defining the stability of each of these. And I would encourage you to practice this on your own too, because once you get the hang of it, now that's another tool in your toolbox, another way that you'll be able to analyze stability of equilibria points without having to get out a calculator and do test points and stuff like that. Okay? Let's start with number 1. Like before, when the blue is bigger than the red, that means we are increasing. And when the red is bigger than the blue, that means we are decreasing. Okay? It's as easy as that. You see, this is a lot more fun than doing all that junk with the test points. And did you notice that I don't have numbers for R and K? You can't really do the method of test points if you don't have any numbers, right? But I'm doing this conceptually without any numbers. So that's another bonus. In this region between 2 and 3, the blue is above the red. So that means this is bigger than that. And so I have rightwards movement. And in this case over here, all the way over here, the red is bigger than the blue, and so I have leftwards movement there. Okay, and so now I'm going to take this and I'm going to put it on my phase line there. Like I was saying, it goes up, down, and that allows me to classify the stability right away. I can see that this one is stable, this one is unstable, and this one is stable. And as usual, dynamics on a one-dimensional line, stable and unstable equilibrium must always be separated between each other with equilibria of the opposite type. You see it goes stable, unstable, stable, unstable. You can't have two stable ones right next to each other. That would make their basins of attraction really confused, right? Oh yeah, remember we learned about basins of attraction? If you want to review that a little, you could consider where's the basin of attraction for the lower fixed point, what's the basin of attraction for the higher fixed point, and you'll notice that the unstable fixed point in between is what separates the two basins of attractions. So basically, if I start with a number of budworms that's less than 2, then less than whatever this value is marked to, then I'm going to go towards the low population. But if I start with a population that's greater than what's located at the second equilibria, then I'm going to go towards the higher, really high actually. Look at how high this x is. Look at how high that value of x is compared to what was previously the only stable equilibria. And now you know why it's called the Spruce Budworm Outbreak, because that's the outbreak zone. This is the type of situation dynamically where there's a possibility of an outbreak in this species where we're going to have a population that ends up being really high here. And notice that you don't have to start necessarily with a ton of budworms to get there. You just have to be in the zone where the amount of budworms you have is greater than this level. And then it's going to shoot over to this outbreak zone. Wow. That is completely different from case 1, and that's why in between case 1 and case 3, we have some kind of bifurcation. And it is a saddle node bifurcation because what happens is that somewhere in between here, these two equilibria get born. Okay, at some point right in the middle at the bifurcation point, these two equilibria are going to be merged together, and they're just going to be one thing, and then they just split apart as I increase one of the parameters. Okay, so let's take a look at, my bad. This whole time I had it labeled as case 2, but that was actually case 3. Oops. So I hope that you're following along and you'll notice that. This is case 3 right here, and now we're going to rewind a little bit and we're going to consider what's case 2. Case 2 is going to be a place where we just have 2 equilibria points located on this graph. And now as a challenge mode, let's erase this, and I challenge you on your own page, if you're playing along, I challenge you to try to draw a case where you have the blue line intersecting the red line exactly 2 times. That's the hardest case to draw, so of course I saved it for last. But you try to do it too. Hopefully you're playing along. And I will do it as well. Now we're going to be in case number 2. And how many equilibrium points we're going to have is 2 equilibrium points there. Okay, so this is case number 2. Were you able to do it? Did you figure out what kind of blue line would intersect this red line exactly 2 times? You see, that's tricky business because I can draw a lot of blue lines that would just intersect it once, right? And likewise, I can draw a ton of blue lines that are more shallow and that would surely intersect it 3 times because this red line goes on forever. Remember that this red part of the function has a horizontal asymptote at 0. And so if I draw a shallow line, surely the blue line is going to intersect the red 3 times. But to make it intersect it twice, what am I supposed to do? I have to mess with the slope of the line so that it just grazes this little inflection point right here, just grazes it, just touches it, and it's kind of like a tangent line. Remember when we learned calculus? Consider that at the location of the inflection point in this part of the graph, I'm going to draw a line that just grazes the function right there. And then, of course, it's going to go through it once up here, too. And that is the exact instance in which I'm going to have 1 equilibrium there and 1 equilibrium there as well. That's the bifurcation point. That's the point at which a saddle node bifurcation occurs. And as we explore more and more bifurcations, you'll see that a theme emerge. Is that every time we're exactly at a bifurcation point, we seem to have one of those semi-stable equilibria, which is not quite stable and it's not quite unstable. In fact, it's a little bit of both. It's a little bit of both in each direction. It's a node. And so that's why it's called the saddle node bifurcation, is because at the moment of birth, right here, where these, what's going to become 2 equilibrium points, right at the moment where they're born as 1 point, just grazing the function, it actually, the stability turns out to be a node. So let's analyze that for case number 2 so that we see this happen, okay? And just like cases number 1 and 3, we're going to have some low value of x star that I'll label that as 1. And then in case number 2, we're going to have this second point emerge right here. And so on that diagram there, we can just label that as 1. And then we can label that one as number 2 right there, right? But you'll notice for this middle phase line of case 2, I haven't put the arrows on it yet. Definitely encourage you to play along. And if you want, it will be a great exercise to pause the video right here and try to draw what you think I'm going to draw for the arrows by applying the over-under method right now. Okay? And it's as easy as just figuring out who's on top and who's on bottom. And so you can see that when I'm in the low X category, blue bigger than red means I'm going to go to the right. In this category between number 1 and 2, red bigger than blue means I'm going to go to the left. And then in this category where I'm greater than the number 2, because the blue line is just grazing the red line and it's not actually going through it twice, like in case 3, I went from red greater than blue and then on the other side, it's still red greater than blue. That's the behavior of a node. You see, red greater than blue means left behavior, and so my phase line looks like this, up, down. So surely this first fixed point is stable, but then on top of number 2, it's also down. So right here in case 2, 2 is half stable and half unstable. So number 2 is a node, and that is typical of a saddle node bifurcation at the point where the pair of equilibrium points is just born. They actually are merged together as one, and the stability of that one point is a node. And then after that point, as they start to veer away from each other and we get into case number 3, that node becomes strictly unstable or strictly stable points. Okay, so we have the node for number 2 right here, in this case, in case number 2, and this case number 2 is the case of the saddle node bifurcation. Okay, so I'll just write that for good measure to make sure that you understand the conclusion here is that the saddle node bifurcation occurs at case number 2. Saddle node bifurcation occurs at case number 2. Okay, now for the other video that I had on transcritical bifurcations, I actually drew you a bifurcation diagram. That was a really fun diagram because what it did was it took the phase lines like this and it lined them all up where the x-axis was the parameter that I was varying. You may have noticed that I didn't do that for this case, and that's because as I manipulated the blue line here, I was changing maybe R, maybe K, maybe both. There's actually 2 parameters here for me to play with. There's R and K, and they both have a very important biological meaning. R is the growth rate and K is the carrying capacity. If I was going to make a bifurcation diagram for this example, I would want a bifurcation diagram that illustrated the effects of both R and K on the system, and that's 2 parameters. So my bifurcation diagram would be 2-dimensional in the parameter space. Just like what we've learned so far, everything gets trickier when you move up to 2 dimensions, and so does bifurcation diagrams. So do they. They get more complicated. So I'm just going to show you the bifurcation diagram in the book so that you get an idea of what a 2-dimensional bifurcation diagram is. Now I'm not, oh sorry, the thing's really shaky. I'm not saying that the dynamics is 2-dimensional. I'm saying that the number of parameters that we're studying is 2-dimensional. And so you can see that one parameter is the R, the growth rate, and the other parameter is the K, the carrying capacity. So the bifurcation diagram is complicated because it's varying 2 parameters at once. But what you see there is you see the different instances. Here's the instance where it's just refuge. That's the low steady state. Then there's the instance here where it's bistable. That's what I was calling case 3. And the dividing line between cases 1 and 3 is this line right here. And then there's a whole nother dividing line here where there's another case up here. I might call that case 4, where that's outbreak only. Actually, I didn't do that one on the board here, but if you wanted to know what case 4 would look like, it's kind of like case 1 in that it only has the one fixed point, but it's different than case 1 because it has a really big value of x at that fixed point. Okay, so let me just draw case 4 as well. Remember that case 1 was the case where my blue line went like this, and so I had only one equilibrium point that was stable, and it was for a low value of x. Now, another challenge for you. Can you draw a blue line that intersects the red line just once, not 2 or 3 times, just once, but where it intersects the red line, it has a really high value of x instead of a low value of x? Remember case 1, I drew the blue line like this, and the intersection point had a very low value of x. Try it. I'll try it too. Sure, why not? What if I drew my line like this? How about that? If I drew my, well, it doesn't really look like a line. I made it a little too curvy. But let's see. What if I drew my line like this? Right? So if I had a line that had a sufficiently high slope and a sufficiently high intercept over in the horizontal axis there, then I would only have one equilibrium point here where this is a very large value of x, as opposed to case 1, that was a low value of x, and what I'm going to call case number 4 is one equilibrium point with a high value. You see? The value of x here is really big, and so that's what they're calling outbreak only. And so if you're in a parameter situation, your values of r and k are such that you're only going to intersect the line all the way over there, then all you have is outbreak. If you're going to intersect the line 3 times, then you could either be in a low population or a high population zone, and those two zones are going to have different basins of attraction separated by the unstable equilibrium in the middle. And then if you're over here in case 1, then all you have is a low population. There's so many different things that this seemingly little model can do, and it's because we have the power of bifurcations to analyze it. Once again, I want to show you not only the two-dimensional bifurcation diagram that describes the different cases. Once again, I'll just point them out in my video. Refuge only was case 1. Case 2 was the dividing line between refuge only and bistable. And then case 4 was outbreak only. Case 3 was bistable. What I called case 4 was up here, outbreak only. And of course, there's another case, which is the dividing line between bistability and outbreak only. I guess I could try to draw that too. Okay, so the dividing line between bistability and what I called case 4 here might look something like this, where it grazes it just once on top, and then it hits it again over there. You see? So there's some sort of another saddle node bifurcation where it takes away the 2 lower fixed points, the 2 equilibrium points that were down here. If you raise up the line, those 2 will merge together and to the location of the tangent point there, and then they will disappear. So many interesting bifurcations, and there's lots of other ways to analyze this. Alan here is referencing Stephen Strogat's book from 2014, one of my favorite texts on nonlinear dynamics by Stephen Strogat's there. That's who had that original Romeo and Juliet model too. So fun, so definitely check that out, Strogat's 2014. If you want to go further into the analysis of this, I also made a Desmos graph so that you can play with the parameters and you can see all the different cases. So check the description of this video for a link to that graph and play with it yourself.